All right, guys, test 1 is over. We're starting material for test 2. And we start test 2 here in chapter 4. Now, in chapter 4, we're continuing on and are looking at just the motion and description of the motion, kinematics. Here in chapter 4, we're going to move from line motion along a straight line, to motion in a plane, so 2 dimensions. So we're going to be talking about trajectories, okay? Things that are fired like a bullet or a cannonball or a baseball or a tennis ball, and comparing that and also looking at motion in circular pathways, circular motion, any kind of motion that has both an X and a Y component. So just to review, remember that our position vector, vector r, in 2 dimensions is a vector that points from the origin to a location in space. So the position vector in 2D motion is going to have both an X component and a Y component. Okay? It's going to have both an X component and a Y component. Let's scroll down. So if we look at this trajectory, our pathway in an XY coordinate system, okay, if we're at this position here, there's going to be an X component of the R vector and a Y component. So I could give that location by giving components, XY, or we could give it by angle and length of the R vector, okay? Now, delta R, change in position, then is going to be a vector that would point from one point to another, okay? And it would have X and Y components. And we know that velocity is change in position with time. So if the delta R vector has X and Y components, it makes sense that velocity is going to have X and Y components. So let's think about this motion diagram in 2 dimensions and think about average velocity versus instantaneous velocity. Okay, now I'm going to scroll up a little bit so we've got the whole image. Okay. Now, if this was my initial position and this was my final position, the vector that we see here is our delta R vector, okay? And then if I change my 2 position here, notice how the direction of the delta R vector changes. And here, it changes still. What we're kind of looking at here, looking at these series of vectors, is letting delta t approach 0. And we know as delta t approaches 0 that what we're going to get is a tangent line. Okay, so the velocity vector at a point in time runs along the tangent line. Okay, let me say that again. The velocity vector as delta t approaches 0 is going to point along a tangent line to the curve. Okay? It's not related to the slope of the curve, but it is related, its direction is based on the tangent line. The acceleration vector is a change in velocity with time, so acceleration, just like velocity, should have an X and Y component, and the instantaneous velocity vector should point in the direction of delta V as delta t approaches 0. Okay? Now, note, up until this point, we've looked at cases where we have constant acceleration. You can have an acceleration that is changing. Acceleration could be changing in, and that should say magnitude. Let me change that. Acceleration can be changing in magnitude and changing in direction, or both. Just like velocity could be changing in magnitude or direction, or both. Now we know that we would get acceleration vectors graphically by looking at v final and v initial, and we know that delta v, which is v final minus v initial, would tell us the direction that the acceleration vector points. Now, acceleration always points in the direction of delta v. We're going to look at figure 4.1. If we look at that, if we look at drawing 4.1, what we see is that our velocity vectors point from one point to another. Okay? So this object is moving in a circular pathway. And if we looked at v final minus v initial, okay, v final, so if I took this as v final and this is v initial, you know, I'd have to come back here and put it in. What we get is a vector that points toward the middle. Oh, that's working pretty good today. So what we notice here is in this situation, the velocity vectors, the acceleration vectors are always pointing in toward the middle. This is a type of acceleration that we call centripetal acceleration. Centripetal means center seeking. Okay? Notice that these velocity vectors are all the same length. So the magnitude of the velocity is not changing. What's changing in this situation is the direction of travel. What I want you to get out of this is notice that these acceleration vectors are essentially perpendicular to a tangent line to the circle. When the acceleration vector is perpendicular to the velocity vector, all it does is change the direction of the velocity vector. It doesn't change the magnitude. Okay? So, they're not changing the speed, we're only changing the direction. So this is a big hint. Only the portion of any acceleration vector that is perpendicular to the velocity vector does not change the magnitude of the velocity. All it does is change the direction. So let's look at this image. Okay, so here we can see acceleration is parallel to velocity, so the velocity vectors are getting longer. Here it's at an angle, but it's not at 90 degrees, so a portion of it goes to making it longer and a portion goes to turning it. Here again, a portion increases its length, a portion is perpendicular till it turns it. Here it's perpendicular, so notice this velocity vector and this velocity vector are the same length. And here now, okay, is starting to, if I compare this one to this one's a little shorter and it's turned, a little shorter and it's turned, and now they just keep getting shorter. Okay, so this would be an object rolling down a hill into a valley and up the other side. Okay, so that acceleration vector, the component of the acceleration vector that's parallel to the velocity vector increases or decreases its magnitude. The portion of the acceleration vector that's perpendicular to the velocity vector changes the direction of travel. Okay? So, it would be rather complicated for us to describe two-dimensional motion by talking about velocity vectors and accelerations being perpendicular or parallel to that trajectory. So we want to get into a method of dealing with two-dimensional motion that is going to be useful and easier to deal with. So we're going to set up a Cartesian coordinate system where every position vector is going to have an x and y component. so that every velocity vector can have an x and y component, so that every acceleration vector has an x and y component, and we can look at the overall motion as the sum of a x motion and a y motion. Okay? So again, we've got that trajectory. We're going to start breaking positions up into x and y coordinates. And we can say that the r vector is equal to rxi plus ryj. This means that the velocity vector, delta r delta t, is delta rx delta ti plus delta ry delta tj. So we have an x and y component of velocity. And we know that magnitude and direction of velocity vector, we can think of it as in component forms. And if we know the magnitude of the velocity and the angle it makes with the x-axis, we can say velocity in the x direction, its magnitude is equal to the velocity times the cosine of theta. Vy is equal to v sine theta. Again, we're using right triangle stuff. And if we want to undo, we would know the magnitude of the velocity equals the square root of vx squared plus vy squared, and the angle theta from an x-axis is equal to the inverse tangent of vy over vx. Okay, we can go through the same thing for acceleration. Acceleration in the x direction is delta vx over delta ti. Ay is equal to delta vy delta t over delta tj. Okay, which gives us the following set of equations. Now guys, these are just the equations we were using with 1D motion, but now we've written them for x and y. So, there's your three equations, just written in terms of x and y. And we're going to look here, the starting problem, looking at problem 6 on page 105 in your textbook. Now this is one of the embedded problems. Okay, so problem 6. All right, now let's read the problem and let's work it. Got a good shot of the screen there. Now, if we read problem 6, it says, come on. No, it says I'm gonna shoot this. Let's see if I can get the document cam to work. Doc cam. Okay, let's scoot this back over here because this is a graphing thing. I think we need the doc cam. Okay, let's look at problem 6 here. Yeah. Now, it says a rocketed hockey puck moves on a horizontal frictionless table. Figures 4.6 show graphs for velocity in the x direction, velocity of the y direction as a function of time. The puck starts at the origin. In which direction is the puck moving at t equals 2 seconds? And then how far from the origin is the puck at 5 seconds? Now, let's look at this graph, okay? There is an x component here for the motion, and there is a y component here for the motion. And we've got velocity versus time graphs. So at t equals 2 seconds, if I look here, okay, at 2 seconds, the velocity in the x direction seems to be 15 centimeters per second. Vx is equal to 15 meters per second, and that's positive. Okay? If If you look at Vy, it's equal to 30 meters per second, and that's positive. Now, let's slide over here for a sec. Okay? So that means the magnitude of V is just going to be the square root of 15 centimeters per second squared plus 30 centimeters per second quantity squared. So let's plug it through. 15 squared plus 30 squared, square root. So I get 33.5 centimeters per second. If we want to get the angle theta, it's going to be the inverse tangent of 30 divided by 15. So I get theta to be 63.4 degrees. So 63 degrees, so if I was to draw this, I would have 63.4 degrees here, and that would be my velocity vector. Okay? Now that's part A of the problem. Now, if we look at this again, part B of the problem says how far from the origin is the puck at 5 seconds. So now our time is 5 seconds. Okay? If I look at a velocity versus time graph, the position, okay, the location can be gotten by looking at the area underneath the curve. So our x position is 5 times 40 divided by 2, because that's a triangle, 1/2 base times the height. So our x final position, assuming that we started out at a 0, okay, would be 5 times 40 divided by 2. So x final would be 100 centimeters. Okay? Y final would be, we've got a rectangle here. I've got 5 times 30. So it's plus 150 centimeters I. Okay? So that's all the information off the graph. So if I want to know R, the magnitude of R, it's just going to be the square root of 100 centimeters squared plus 150 centimeters squared, square root. So 100 squared plus 150 squared, take the square root, I get 180 centimeters. Now, it just asked us how far from the starting point we were. But if we also wanted to get the angle theta, it would be the inverse tangent of 150 divided by 100. So I get 56.3 degrees. So that would be our location from our starting spot, assuming that we were measuring from our origin. Okay, so there's a really simple equation, again letting us use our graphs. Okay, now let's talk projectile motion. Projectile motion is the most common type of two-dimensional motion we're going to deal with. It's motion in 2 dimensions under the influence of gravity and gravity only. This is an object that's in free fall that had an initial horizontal component to its velocity. So if I rolled a ball off a table, or a bullet after it's fired, or a cannonball that's been shot, or a baseball that's been hit, a package being dropped out of a plane, all of these things would be considered projectile. Once it is launched, okay, it's under the influence of gravity and gravity only. All projectiles follow a parabolic trajectory. All objects undergoing projectile motion are launched, given some kind of initial velocity at some angle to the horizontal. The angle at which it is launched is just called its launched angle, okay? And the angle is measured from the horizontal along the object's initial, from the horizontal to the object's initial velocity vector. So projectile motion is made up of two independent motions, an X motion and a Y motion, that are linked through time. Okay? So here's a basketball that was thrown. It had an initial velocity v0. It's going to have an x component. v0x is equal to v0 cosine theta. v0y is equal to v0 sine theta. And it's going to follow this parabolic pathway. Okay? The velocity in the x direction is going to remain constant. The velocity in the y direction over the course of travel is going to change. We know this because notice it has a turning point here where it stops going up and it starts coming down. So there's a turning point. The horizontal motion has an acceleration of 0. The vertical motion has an acceleration of minus g, minus 9.80 meters per second squared. It went a little wild there. Okay, so for the x-axis, we can say Vx equals V cosine theta, x final equals x initial plus Vx delta t. For the y motion, where we have an acceleration, we're going to use those uniform acceleration equations. We say velocity in the y direction initially is equal to V sine angle of launch. V final y equals V initial y plus AY delta t. Y final equals Y initial plus V initial y delta t plus 1/2 AY delta t squared. And then V final squared equals V initial squared plus 2A delta y, where A is minus 9.80 meters per second squared. Okay, our basic equations here. So if we look at this pretty graph, okay, this is a motion diagram for an object undergoing projectile motion. So notice velocity initially y, velocity initially x at time 1 second, at time 0. Here at 1 second, notice velocity in the y has decreased, velocity in the x has stayed constant. Here, all we have is the velocity in the x, velocity in the y has gone to 0. Now, velocity x still 9.8, velocity y is now minus 9.8. And if we got down to here, come on, roll up for me. It doesn't want to. I hate this thing. It was working so well earlier. Come on, go up for me. Well, guys, give me a second. I gotta walk over here to the computer and roll this to where I want it. all of our equations. What did it do? Okay. So there's the graph we were just looking at. Okay? Now, let's say that we were firing at a coconut, and at the instant we fired, the coconut were to drop. Okay? Now, there's our sight line. But because our arrow, or our bullet, experiences acceleration due to gravity as it falls, its trajectory turns. Okay? If the coconut is dropping at the same, dropped at the exact same instant that we fired our bullet, turns out that the bullet and the coconut would meet up, because over that time window, they would have both experienced the same amount of acceleration due to gravity in the negative direction. I usually can do this for you in class and show you, but we're not in class. I'm having to do this on video. So let's talk about problem solving. Projectile motion, problem solving. Okay, you want to make a simple model, treating your particles as if they're point masses, your objects, and ignore air resistance for right now. You're going to want to do some kind of pictorial representation. You want to establish a coordinate system, an x-axis and a y-axis. It's very important to do your sketch and kind of lay things out on there and put all the information that you need or you can get onto your pictorial representation. You want to solve, when you get ready to solve, you want to remember the acceleration in the x direction is 0, acceleration in the y direction is minus g. So you end up with two one-dimensional kinematic problems that you're trying to solve simultaneously. And your kinematic equations, this is out of your book, is x final equals x initial, v initial, x delta t. V final equals x equals v initial x, which equals a constant. Y final equals y initial, v initial y delta t, minus 1/2 g delta t squared. V final y equals v initial y minus g delta t. Delta t for the horizontal and vertical components are linked. So, you're going to have an x position at a time, you're going to have a y position at a time. And check your results, has correct units and is reasonable and answers the question. So we're going to spend the rest of our time right now looking at problem solving. And we're going to look at problems at the end of the chapter. Now, next time you're in class, okay, I'm going to be giving you hard copies of these problems. So you might want to stop watching my lecture right now and then come back and start this back up when you've got the hard copies. Okay? If not, continue on. Now I'm going to switch over to the camera. Okay? And we're going to start off by looking at problem 13. So let me scoot it over this way. Problem 13. Now, it says a supply plane needs to drop a package of food to scientists working on a glacier in Greenland. The plane flies 100 meters above the glacier at a speed of 150 meters per second. How far short of the target should it drop the package? Okay, guys, let's start looking at how we'd approach this. Okay. Okay. Oh, this looks pretty good. First thing I want to do is I want to identify what I want to find. And I want to find x initial, and it's going to be in meters. So x initial here is where the plane lets go of the package. And it's got a velocity initially of 150 meters per second, and that velocity initial is parallel to the ground. Its y initial position is 100 meters. We know that y final is going to be 0 meters, and x final is going to be 0 meters. Okay? I am assuming that it's traveling in the positive x direction. So x initial, I want to find out when x final is 0. Velocity initially in the x direction is 150 meters per second. Acceleration in the x direction is 0. Velocity in the y direction is 0. Acceleration in the y direction is minus 9.80 meters per second squared. Y initial is 100 meters. Y final is 0 meters. Now, we have the most information about the y motion. So I'm going to work with the y motion first and try to find the time that it takes to hit the ground. Okay, so if we scroll up here, it says I'm going to find the time to hit the ground using the y motion. So y final equals y initial plus v initial delta t plus 1/2 ay delta t squared. So 0 equals 100 meters plus 0 delta t plus 1/2 times the minus 9.80 meters per second squared delta t squared. So take the 100 over, minus 100 meters equals minus 4.90 meters per second squared delta t. We solve for delta t, we get 2.26 seconds. So I now have time. Notice how I box that in. Every time you solve for something, I want you to box it in. And I want your problems to be laid out in this kind of neat, orderly fashion. Okay? Now, once I have the time, I can use the x motion to find x initial. Well, I wrote out the whole equation, okay? Just in case you didn't remember. So x final equals x initial plus v initial x delta t plus 1/2 ax delta t squared. So I have 0 equals x initial plus 150 meters per second times 2.26 seconds plus 1/2 times 0, ax is 0, times 2.26 seconds squared. So I get 0 equals x initial plus 339 meters, so x initial equals a minus 339 meters. Okay? Now, remember, the way we solve a problem is critical. So we're going to move on, and we're going to look at problem 50. Okay? Problem 50 is on page 107. Down here, problem 50. Ah, there it is. Says a ball is thrown towards a cliff of height h with a speed of 30 meters per second and an angle of 60 degrees above horizontal. It lands on the edge of the cliff 4 seconds later. A, how high is the cliff? B, what is the maximum height of the ball? And what is the ball's impact speed? Okay, so let's look at how we're going to solve this problem. Sorry, guys. I'm going to start off by putting information out. Okay, start with my drawing. I'm going to launch at a velocity initial at our angle. And it's going to go up and it's going to land on the edge of my cliff. Okay? So I know that if my magnitude of my acceleration is 9.80, velocity initially is 30 meters per second, our angle of launch is 60 degrees, it's 4 seconds to go from initial point to final point. y initial is 0, y final is not given to us, okay? We also don't know x final. So what we're going to be looking for here is y final, y max, and velocity final. Now, given our initial velocity in the angle, I can get velocity initially in the x direction is 15 meters per second. That's its magnitude. Velocity initially in the y direction is 26 meters per second. These are things that you should do before you do anything else in the problem. Get all of this drawn and established. Okay? Now, first thing we were asked to do is find y final. Well, we know y final equals y initial plus v initial y delta t plus 1/2 ay delta t squared. So y final is equal y initial, which I made to be 0, is equal to 26.0 meters per second squared, meters per second times 4 seconds plus 1/2 times the minus 9.80 meters per second squared, 4 seconds squared. If you solve that, you get y final is 25.6 meters. Okay? Now, step 2, the second thing we were asked to find was y max. Well, I'm going to use one of my favorite equations. V final y squared equals v initial y squared plus 2ay delta y. So I've got 0 squared equals 26.0 meters per second squared plus 2 times the minus 9.80 meters per second squared delta y. Delta y is 34.5 meters, so y max minus y initial equals delta y. Y max minus 0 equals the 34.5 meters, so y max is 34.5 meters. Okay? Now, step 3 of the problem wants us to find v final. Well, I know that v final x equals v initial x, which is 15 meters per second. V final y is going to equal v initial y plus ay delta t. So I get 26 plus a minus 9.80 meters per second squared times 4 seconds. I get a minus 13.2 meters per second. So in other words, it's come up and it's going down when it hits the cliff. So v final in magnitude is going to be 15 squared plus a minus 13.2 meters per second squared. So I get 19.98, rounding it to 3 significant figures, I get 20 meters per second as the speed at which it hits the cliff. It doesn't ask us velocity, the problem asks speed. Okay? Now, let's move on to another problem. We're going to look at problem 55 on page 108. Okay? I'm learning how to line things up with this document cam. It's not my normal setup. Wrong way. Okay, let's look at problem 55 there. It says you're 6 meters from one wall of a house, shown in 4.55. You want to toss a ball to your friend who is 6 meters on the opposite wall. 6 meters from the opposite wall. The throw and the catch each occur 1 meter above the ground. What is the minimum speed will allow the ball to clear the roof, and what is the angle you should toss the ball? Okay? Now, here's our drawing. I'm just going to build upon this drawing. I'm just going to do a simple version of that drawing to get us started. Okay? So, 6 meters, 6 meters, 6 meters. So we've got 18 meters from thrower to thrower. So I'll make this my x initial. My x initial is 0, y initial is 1 meter. Y final is 1 meter, X final is 18 meters. Okay? I know that they told us that this was a 45-degree angle and this was 3 meters to halfway, so that's 3 meters. So the maximum point of the house is 9 meters. So essentially my ball has to, at its Y max, has to be at we have to be at 9 meters. So I'm going to work with Y max first, okay? So if we look at Y max, at our maximum height, I know the velocity final in the Y direction is going to be 0. So I'm going to use V final Y squared equals V initial Y squared plus 2AY delta Y. So 0 squared equals V initial Y squared plus 2 times a minus 9.80 meters per second squared times 9 meters minus 1 meter, because remember we're launching from Y initial is 1 meter. So solving that, I get Y initial to be 12.5 meters per second. Now that's its magnitude, but we know from our drawing that we're launching up. Now, moving on, I know at the catch point, V final Y is going to equal V initial Y because they're at the same height. Now you can check me out on that, but I swear, cross my heart. Okay, so we know that V final Y equals V initial Y plus, well, they're going to have the same magnitude, but one's going to be negative, one's going to be positive. V final Y equals V initial Y plus 2AY delta T, so minus 12.5 meters per second equals a plus 12.5 meters per second plus a minus 9.80 meters per second squared delta T. If we solve that, I get the time of flight to be 2.55 seconds. And I forgot to write my seconds there. I apologize, guys. Okay? Now I can say that X final equals X initial plus V initial X delta T. So 18 meters is equal to 0 plus V initial X times 2.55 seconds. So V initial X is 7.06 meters per second. And now I can say the velocity initially is the square root of 7.06 meters per second squared plus the 12.5 meters per second squared, or 14.4 meters per second. And its angle of launch is the inverse tangent of 12.5 divided by 7.06, so 60.7 degrees. I didn't bother to write the units in here because they're going to divide out. So we've got the magnitude of the velocity and the angle of launch. Okay? Now, if we move on to question 56. Okay? It says sand moves without slipping at 6 meters per second down a conveyor that is tilted at 15 degrees. The sand enters a pipe just below the end of the conveyor belt, as shown. What is the horizontal distance D between the conveyor belt and the pipe? Okay, now we've got figure 4.56, and we're going to kind of rough sketch it. Okay, you always need a rough sketch on your paper. Okay, so there's our conveyor belt, there's our velocity initially pointing down the conveyor belt, and that's a 15-degree angle. Velocity initial is 6 meters per second. We're going to be heading out a D to the pipe, and the pipe is 3 meters below. Y initial is 3 meters. Y final, I'm making 0. So I'm making my 0 vertical position at the top of the pipe. I'm making X final 0 and Y initial I want to know, X initial I want to know. Okay? So velocity initial in the X direction is 6 cosine of 15, or 5.80 meters per second. Now remember, in you know, if I were to extend this line out here and do that line, opposite angles like that are going to be equal. So that's why I can use 15 degrees. Velocity initially in the y direction, its magnitude is going to be 6 sine of 15, or 1.56. Now, we know the most about our motion in the y direction. I know our initial position, final position, I know the acceleration, I know the initial velocity. So we're going to look at the y motion first. Hint, 99% of the time we look at the y motion first. So if I look at the y motion first, I know velocity initially in the y direction equals a minus 5.6 meters per second. It's negative because we know that velocity vector is pointing down. Y initial is 3 meters, y final is 0. The AY is minus 9.80 meters per second squared. So I want to find delta t. So if I solve for delta t, notice that I am, when I plug into the y final equals y initial plus v initial delta t plus 1/2 ay delta t squared, that I get an equation that's got a delta t and a delta t squared. I've got a quadratic. Guys, sometimes you just have to use the quadratic. If I rewrite this in ax squared plus bx plus c form, I get a minus 9.80 delta t squared minus 1.56 delta t plus 3 equals 0. Now, delta t then would equal a negative of a minus 1.56 plus or minus the square root of minus 1.56 squared minus 4 times a minus 4.90 times 3, all over 2 times a minus 4.90. There is a solution when I add, there's a solution when I subtract. One of my answers is minus 0.958 seconds. The other one is a 0.639 seconds. We can't have a negative time. It doesn't go back in time, so we have to go with our positive answer. Our answer is 0.639 seconds. Okay? So one of them isn't going to make mechanical sense. So if I then go and use the equation x final equals x initial plus v initial x delta t, I get x final equals 0 plus 5.80 meters per second times 0.639 seconds. So I get x final to be 3.71 meters. That means that the distance between the conveyor belt and the pipe has to be 3.71 meters. And I go toward the middle of the pipe. Okay? Now I wanted you to see that one because we had to use the quadratic. And that, guys, are the example problems that I've got for you on projectile motion. Okay? We could do a whole lot more, but I'm sure you're going to get bored watching me do problems. Okay. Now, we're going to take a brief look at relative motion. Relative motion is the description of an object's motion relative to the motion of something else. Okay? And we want to start by defining an inertial reference frame, which is the reference frame that is not accelerating. So its velocity is constant. Could be sitting still. It could be moving at a constant velocity. Okay? So what we're thinking of here is comparing what two different observers of a same event see and how they would describe it. So if I were to take something I can throw and catch. Okay. So if I were to take my drink bottle here, and I were to just throw it up and down, okay, I'm not moving. You guys and me, we both just see it going up and down. But if I now walk and throw it up and down, from my point of view, it just went up and down. From your point of view, it made a parabolic, well, it followed a parabolic pathway. There was a difference. All right? So where you're observing from is going to affect how you describe the motion. We have one reference frame moving relative to the other reference frame. Okay? So we're going to have a reference frame XY, which is stationary, and a reference frame X prime, Y prime that is moving at a constant velocity. So there's a Vx for the reference frame, a Vy for the reference frame. So if I look at the position in the moving reference frame relative to the position in the stationary reference frame, they're going to be related by the position of the moving reference frame relative to the non-moving reference frame. That's a mouthful. So there are equations that relate things. The position in the non-moving reference frame is equal to the position in the moving reference frame times its velocity times the time, since the two reference frames were one on top of each other. So I can say X in the non-moving equals X prime plus the velocity at which the reference frame is moving plus delta t. Do the same thing with Y. Vx equals Vx prime plus the velocity of the reference frame. Vy equals Vy prime plus the velocity of the reference frame. So we're going to look at problem 20 on page 106 at the end of the chapter. Now, if we look at problem 20, it says, Mary needs to row her boat across a 100-meter wide river that is flowing to the east at a speed of 1 meter per second. Mary can row with a speed of 2 meters per second. If Mary points her boat due north, how far from her intended landing spot will she be when she reaches the opposite shore? And what is her speed with respect to the shore? Okay? Now, if we take the shore to be her, the non-moving reference frame, her velocity in the y direction, well, here, I'm going to draw a picture and then we're going to look at it. And then we'll come back and look at those. Okay. Okay. So our initial reference frame, XY. Okay, this is the riverbank. We know that she's starting out here at x equals 0, y equals 0. Okay? And we know that our reference frame x prime and y prime has a velocity Vx of, let's see, what was it? Vx was given to us as 1 meter per second. Okay, now her boat is traveling in this reference frame with a velocity Vy of 2 meters per second. Its Vx, and this is prime, is 0. Okay? And we are headed to a position of going across the river 100 meters. Now that's in both reference frames because this one's only moving in the x direction, okay? The velocity of the reference frame y is 0. Okay, so I've kind of set it up for you. Now, so velocity in the reference frame is 2 meters per second. Y final is 100 meters in both. Velocity in the moving reference, the velocity of the moving reference frame is 1 meter per second. So the velocity in the stationary frame is 0 meters per second plus 1 meters per second, or 1 meter per second. Y final is 100, so 100 equals 0 plus 2 meters per second delta t. We get 50 seconds. So x final is equal to 0 plus 1 meter per second times 50 seconds, or 50 meters. So she ends up 50 meters down the river from the point that she initially launched from. Even though she was paddling due east, the river took her 50 meters downstream. Okay? Now, that is a good stopping spot, and we'll pick up with uniform circular motion next time.